Alright, so we're going to get started with this online lecture on combined loading. If you recall, in our previous lectures we've discussed the concept of stress analysis and ideas like stress transformation, stresses at different orientations, and ultimately principal stresses, maximum shear stresses, and how we can represent those with Moore's circle. So what I'm going to do today in this video is go through some combined loading scenarios that takes what we've learned in previous lectures with axial loads and torsion and bending, and then combine that with our stress analysis concept to sort of create a complete picture, sort of tying those concepts together. So with that, let me go ahead and just jump right into it. So when we look at combined loading, we're going to look at two different scenarios. We're going to look at just beams and frames and structures similar to that, and then we will look at a very specific combined loading scenario when we come back from Thanksgiving break, and that's looking at thin-walled pressure vessels. But basically the idea behind these examples is to assess our fundamental stresses that we've seen before and see how they work when they're in combination with one another. In other words, we know how to assess a shaft, let's say, subjected to torsion. What happens if that shaft is subjected to torsion and it's being bent, and it's being sheared, and it's being subjected to an axial load? How do you handle all of those at the same time? So I have two examples looking at that. The first is this beam. This is a very straightforward problem, similar to problems that we've seen before. And specifically what we're going to look at is what is the principal stress and maximum shear stress at a particular point on this beam. We're doing this problem first because the problem references a lot of the shear and moment diagrams and stress formulas that we've been using very recently. Our next example is going to use some stuff we haven't seen for a little bit for some time. So we'll start off with this one. So I'm going to pull up this this notebook here. Let me go to example 29. Okay, so I have a beam here. The beam is subjected to a point load that's not quite at midspan. It's a little bit off to the right from midspan. And we have here the properties of the beam. What we're going to do is try and determine principal stresses and maximum shear stresses at a point 2 inches from the top. So specifically, if I draw my pen, what we're looking at is we're looking at probably this point right there. Whoop. That point right there. And what we're trying to do is determine maximum shear stress and principal stresses right there. Okay, so in order to do that, we basically have three steps that we need to go through. The first two steps you can sort of do independently, so I'll take these one step at a time. And the first is to actually compute some section properties. Okay, so let's go ahead and do this over here to the right, so section properties. So if you recall, our bending stress equation is sigma equals my over I, or mc over I, and our shear stress equation is vq over ib. Well, we need these values and these parameters in order to compute this. So let's compute a few of these right now. So first off, let's see. So the first thing that we'll need is our moment of inertia, which we have a rectangular cross section that's 2 inches wide and 6 inches tall. So that's just going to be bh cubed over 12. So that's 2 times 6 cubed, and that's all in inches, over 12. And then plug and chug, so that's 2 times 6 cubed over 12. And that's 36 cubic, or not cubic inches, sorry, inches to the fourth. That's inches to the fourth. Okay. Now we know our we know our extreme fiber distance would be 3 inches, but we're not looking at extreme fibers. We're actually looking at the distance from the centroid to the point in question. So really, if remember, our bending stress equation is sigma equals my over I. Okay, and what is y? Remember, y is the distance from the centroid to the point in question. So what we're really looking for, if you look at the beam, we're actually sort of looking for that distance right there. So how far is it from the centroid to the point in question? Well, from the centroid to the very top, this distance right here, that distance is 3 inches. Well, if it's 3 inches from the centroid to the very top, and from the top to the point in question is 2 inches, I propose that y in this case is going to be 3 inches minus 2 inches, so it's going to be 1 inch. Okay. Now, a couple other things. The only other thing that we're going to need is Q. So remember, when you're looking at Q, what we've got is we have a cross section that looks like this. Here's our centroid, and we know that our point in question is right here. So we take that area multiplied by that moment arm right there. So the area is going to be 2 times 2, which is 4 square inches, right? Because that distance is 2 inches, and then that height is 2 inches. As for how far is it from the neutral axis to the centroid, well, it's going to be 2 inches. I think that's pretty obvious there. So our Q is going to be 4 square inches times 2 inches. Again, from the centroid. So from the centroid to the very top, that's 3 inches. And then coming down, that's 1, so that's 2. So that's 8 cubic inches. Okay. And we obviously know, B is 2 inches because we have sigma equals my over I. We have tau equals VQ over IB. So if you look at these stress equations, we basically have all of our properties that we need in order to solve them. The only thing that we're missing is our shears and moments. So we need to compute that out. So in order to do that, we need to draw the shear and moment diagram for these beams. So what we'll need is we'll need to determine what is that reaction BY, and we need to determine what is that reaction AY. So what I'll do is I'll say, let's go ahead and compute support reactions. Okay, and then, it's a little too far. That's pretty good there. So to compute support reactions, what I'll do is I'll sum moments at A in order to determine the reaction at B. So sum moments at A. Okay. So we have AY. We're not going to see any moment contribution from AY. We're going to have our load, 10,800 pounds, acting clockwise at a moment arm of 4 feet. So 10,800 pounds times 4 feet, because from A to B is 6 feet, from B to the load is 2, so that's where the 4 feet comes from. And then we have BY operating at a moment arm of 6 feet. Okay. So I think it's pretty easy to solve for. 10,800 times 4. That's 43,200 foot-pounds is BY times 6 feet. Divide by 6. So we get BY is 7,200 pounds upwards. And if we sum forces in the Y direction, well, I think that's pretty straightforward. If we have 10,800 going down and we have 7,200 going up, the difference between those two is 3,600. So AY has got to be 3,600 going up. And I think by now, with the class, I think we should be pretty comfortable with those calculations. So this is 7,200 pounds. This is 3,600 pounds. Okay. So The reason we need the reactions is because we have to draw the shear diagram and the moment diagram. So let's start with the shear diagram. So draw that out. So we'll say this is the shear diagram and it's in pounds. So what's that going to look like? Well, we start at 0, then we go up 3,600, no change, no change, no change. Then we're at 3,600. We suddenly drop 10,800. So if I'm at 3,600 and I drop 10,800, that puts me at minus 7,200. No change, no change. And then I jump up, back up to 0. So that's the that is the shear diagram. We need the area under the shear diagram to get the moment diagram. So this first rectangle on the left, 3,600 times 4 is 14,400, and then 7,200 times 2 minus 14,400. I think that's pretty easy to assess. So if we have that, we can draw our moment diagram pretty easily. In foot-pounds. Start at 0. Go up to 14,400 linearly, and then go back down to 0. And that's our shear diagram, and that's our moment diagram. So that's the easy part. I guess maybe the more challenging part is to try and determine what are the actual shears and moments at the points of interest. Well, remember, our point of interest is along this MN section. So really what we need to determine are shears and moments along these points here. Well, the shear is pretty simple, okay? So what I'll do is I'll look over here on the right. Actually, let me do that. Okay, so I'll look over here and I'll say from shear and moment diagrams, what we'll do is we'll say the shear along that MN section is just 3,600 pounds. That's easy because if you look at the point in question right here, you're looking at this particular point right there. Well, it's pretty easy to see that the shear is 3,600 right there. It's 3,600 anywhere between A and the point load. So that one's easy. The one that might be a little more challenging is determining the moment. So we know that this shear is 3,600 pounds. This moment might be a little challenging. The way I see it, there's two ways of doing that. What I think is the easiest way is to just use linear interpolation. So for the moment, what we can do is this. We can say, well, this is a line, and so all we have to do is use slope ratios. So if we look at this line right here, if we look at this line, what do we know about this line? Well, let's look at rise over run. We know that we rise 14,400 over a distance of 4 feet. Okay, so I'll write 14,400 foot-pounds over a distance of 4 feet. But instead of 4 feet, I'm going to call that 48 inches. And the reason why is because what I want to do is figure out how far do I rise up over a distance of 9 inches. Remember, if you look up here at section MN is 9 inches from the A support. You can actually raise that up a little bit. See right here, that distance is 9 inches from the A support. So if in 48 inches I go up 14,400, how far do I go up in 9 inches? So you can see that's why I'm using 9 inches down here. So therefore X, or MN in this case, so X is going to equal 14,400 foot-pounds times 9 inches over 48 inches. So that's 2,700 foot-pounds. That's pretty easy. So there's MN. or MN. It's 2,700 foot-pounds. Okay, and you know, there's a like I said, there's two ways of going about that. I think that's the easiest way. The harder way, and I don't really want to say it's harder. It's just, you know, sometimes it can be more work. Is to actually just cut a section and look in either direction in some moments. Now, for this problem, because the loading is really simple, it's really not that difficult, because ultimately when you cut your section and let's say you look to the left, you just have 3,600 times 9 inches. So it's really easy. But if you have more complex loading, that can be a little bit more work. Okay, so now that you have these, what we can do is we can go to our stress computations. This is really easy. Let's take the bending stress first. So we know our moment is 2,700 foot-pounds. We know Y is 1 inch, and we know our moment of inertia is 36 inches to the fourth. So we can compute a stress computation. Before we compute anything, though, if you look at all of your units, we have inches, inches to the fourth, but we have foot-pounds. I'm going to take that 2,700 foot-pounds, and I'm going to convert it into inch-pounds by multiplying by 12. So this is 32,400 inch-pounds. So with these, I can compute a bending stress of My over I, which is 32,400 inch-pounds. 1 inch, and then 36 inches to the fourth. So 32,400 times 1 divided by 36. That comes out to 900, and that's 900 psi. Okay. However, one thing we do want to indicate here is whether or not that is to be taken as compression or whether or not that's to be taken as tension. Okay. So if you go up here and you look at the beam, remember the point that we're looking at is a point above the neutral axis. Remember right here, that's the point in question. And so at the neutral axis we have 0 bending stress, and then above and below we get changes in values. For this beam, remember this beam is going to bend in a smiley face fashion. So in a smiley face fashion, the top is going to be experiencing compression. So you don't really have to worry too much about, you know, positives and negatives really at this point. However, I do think it's really important to say that this is compression. And you'll see why here in a second. Okay, so there's our bending stress computation. Now what about our shear stress computation? Well, we know the shear is 3,600 pounds. We know Q is 8 cubic inches. We know that I is 36 inches to the fourth, and we know that B is 2 inches. So this one's pretty easy. There's no unit conversions that need to be done. We can just plug and chug. Okay, so we have tau is VQ over IB, which is 3,600 pounds. We have 8 cubic inches. We have 36 inches to the fourth. And we have 2 inches. So we plug and chug 3,600 times 8 divided by 36 times 2, and we get 400. So this is 400 psi. So I think it's pretty clear to see that we have not only a normal stress, but we have a shear stress at this particular point. So what those values are and how we assess that is really, really important. So that's where stress analysis and ultimately our concept of Mohr circle and whatnot come into play. So maybe I'll draw a line here to sort of break that up. Draw a line here to break that up. So last thing we need to do is determine principal stresses. And our maximum shear stress. So how we'll do that is this. We need to define a state of stress. Okay. So we need to define a state of stress for this section. Here's what I propose that we do. We have a beam that's being subjected to a load on the top, and we know from mechanics that that's going to generate a normal stress and a shear stress, and we've computed those. So I propose that we're going to have one normal stress value and one shear stress value. So let's take our normal stress. I'm going to take our normal stress and call it sigma x. It really doesn't matter. You can call sigma x or sigma y your normal stress. It really doesn't ultimately affect your answer. So I'm just going to pick one of them, and we'll say that this one is 900 psi. However, in order to ensure that I'm appropriately accounting for my signs, what I'm going to do is I'm going to call this negative 900 psi. And the reason I'm calling it negative 900 psi is because this is a stress that's in compression. If it was on the bottom or below our neutral axis, I'd say it was positive. As for our shear stress, we'll go ahead and say that that's 400 psi. The sign for shear stresses doesn't matter all that much because ultimately you square your shear stresses when you're determining maximum shear stress, so it doesn't really matter whether you take that as positive or negative. And as for sigma y, there are no other stresses on this section. It's not like we have another normal stress. From a mechanics perspective, the only way that we would get a stress, let's say in the y direction, is imagine if I took the beam and I applied, let's say, some sort of compressive load like here and here. Like imagine if I put the beam, let's say, in a big vice grip. If I did that, then I would generate a stress along the y-axis, and I would have a sigma y as well. But we really don't have that in this problem. So really, here's our state of stress. We have our sigma x is negative 900 psi, again taken from sigma equals my over I, and our shear stress is VQ over IB, taken as 400. And so once you have this, determining principal stresses and maximum shear stresses is really simple. We can determine the center of Mohr circle, or sigma average, as sigma x plus sigma y over 2. And see, here's where I was mentioning earlier, it really doesn't matter whether or not we call the 900 psi or the negative 900 psi sigma x or sigma y, because whichever one we put here, we're going to get the same answer. So minus 900 psi plus 0 over 2, so that is minus 450 psi. So that's the center of Mohr circle. The radius of Mohr circle is the square root of sigma x minus sigma y over 2 squared. Again, doesn't really matter which direction you subtract, so it doesn't really matter which one's sigma x and which one's sigma y, plus tau xy squared. So we have negative 900 psi minus 0 over 2 squared plus that squared. And then let's see, so we have so I'm getting 602.1 psi, so that's the radius. So therefore, we can compute our principal stresses and maximum shear stress really easily. We know that sigma 1 is sigma average plus r. We know that sigma 2 is sigma average minus r. And we know that tau max is just r. So I think you can do that pretty easily, and I'm just going to sort of summarize that over here. So sigma 1 ends up being positive 152.1 psi. Sigma 2 is minus 1052.1 psi. And tau max is 602 psi. And that's our answer. And again, I think there's some really meaningful design observations that can be made from this. If all we did was look at these stresses here, for instance, if all we did was look at those stresses, we would see a maximum shear stress of 400 psi, but that's not really the case. At a different orientation, we have a much larger shear stress of 602. So if we, as the engineer, did not perform this analysis in order to determine worst case states of stress, we might have a situation that, you know, it looks fine, but really it's going to fail at a different orientation. So this is an incredibly important analysis. Same thing with normal stress. We have a normal stress of 900 psi in compression compared to a sigma 2 of negative 1052. Again, higher compressive stresses at a different orientation. So again, incredibly important. Okay. I'm going to pause this real quick. Okay. Let's continue on with our next example. So our next example, the analysis is going to be a lot more basic, because instead of making you draw a shear diagram and draw a moment diagram and what have you, I'm just giving you the moment and whatnot for this one, giving you all of the force resultants. However, there's more stresses to consider on this problem and many more section properties. So this one's going to be a little bit of additional work in that regard. So I have a 4-inch diameter circular steel shaft that is subjected to the following loads. So I have an axial load of 18 kips in compression. I have a bending moment of 6,000 foot-pounds and a torque of 10,000 foot-pounds. So same goal as before, determining principal stresses and maximum shear stresses, but there's more stress resultants and components going on. So let's see how this problem plays out. Okay. So the first thing that we're going to do, just like we did on the last problem, is compute section properties, although we're going to need a few more of them. Okay. So okay. So first off, we do need an area. We are going to need an area of the shaft. Now we have a shaft that has a diameter of 4 inches, so it's circular. So the area is pi over 4 d squared. So pi over 4 inches squared. So plug and chug, and that ends up being, let's see, pi divided by 4 times 12.57 inches squared. Okay. We are going to need a moment of inertia. Now if you don't remember these properties right off the top of your head, that's no big deal. You can look these values up in the appendix. The moment of inertia of a circle is pi over 64 d to the 4th. So pi over 64 times 4 inches to the 4th. Now let's see. Okay, that actually numerically comes out to also be 12.57. That's inches to the 4th. Okay. We are going to need a C value. Now a C value is the distance from the centroid to the outermost fiber. So if you have a circle, how far is it from the centroid to the outermost fiber? That's the radius. And so that's d over 2, so that's 2 inches. And last, since we have a torsional component, we are going to need a J value. So that's pi over 32 d to the 4th. So that's pi over 32 times 4 inches to the 4th. And that, I believe, is going to be a little bit of a different value. Yes, I have 25.13 inches to the 4th. Okay. All right. So now that we have our section properties, we can take each of these one at a time, and let's be very consistent. So let's start off with the axial load. Okay, and so the one thing I'll indicate is that's in compression. So we know that if you have an axial load on a section, that the axial stress is P over A. Hence why we needed the A a little bit ago. So that's 18 kips divided by 12.57 inches squared. So plug and chug, so 18 divided by 1.57. So we get 1.43 KSI, okay, and that is in compression, so I'm going to indicate that as such. Okay. Now, next is our bending moment. Now, right off the bat, we have a bending moment of 6,000 foot-pounds. Before we do anything, I'm going to convert that into inch kips, because if I look at my original, or my axial stress, it's in KSI. Let's make sure everything else is in kips and inches. So 6,000 foot-pounds is 6 foot kips dividing by 1,000, and 6 foot kips is 72 inch kips multiplying by 12. Okay. As for our bending stress, we're looking for a worst case scenario so that we know if you have a circular cross section, the centroid is in the middle, so maximum stresses are at the top and the bottom. So the formula is really easy. It's MC over I. So we have 72 inch kips, and we have C, which we already computed up here, is 2 inches. We have our moment of inertia is 12.57 inches to the fourth. So I'm getting 11.46 KSI. Now, the interesting thing about this is, do I take the compression or do I take the tension? Remember, this is a bending stress computation. If you have bending stresses in a section that's symmetric, you get the same value on the top and the bottom, but one's in compression, one's in tension. Do you consider the compression or do you consider the tension? Well, what do you think is the worst case scenario? Remember, here's the cross section, and it's seeing two stresses. It's seeing a uniform stress from the compressive load, and then it's also seeing a bending stress from the bending moment. So the worst case scenario would really be to add these stresses up, not to subtract them. We wouldn't want to evaluate stresses, let's say here at the bottom, where you have 1.43 KSI in compression, but you have 11.46 KSI in tension, because the stresses would be somewhat trying to negate one another. If anything, you want to evaluate the stress at the top, where you have all these compressive stresses adding up together. So I'm going to take the compressive stress side of this, and it's also going to be the same location for where we evaluate the shear stress. So let's take a look at the torsion. Okay, we have a torsion of 10,000 foot-pounds, which is that's 10. That's 10 foot kips, which is 120 inch kips. Well, if you recall from torsion, the worst case torsional stresses are at the outer fibers. So if you're evaluating torsional stresses at the outer fibers and you're evaluating bending stresses at the outer fibers, that's really where you need to be evaluating this for a problem like this. As for axial loads, it really doesn't matter where you evaluate it, because the axial loads are the same everywhere on this section. So we have our torsion. We know that our shear stress equation from torsion is TR over J. Again, this is bringing back those formulas we haven't seen in a while. So TR over J. So that is 120 inch kips times 2 inches divided by the J constant. No, J was 25.13. So let's see. So this is 9.55 KSI. Okay, and since this is a shear stress, it doesn't really matter whether or not it's positive or negative. So therefore, for our state of stress, we have sigma x, sigma y, tau xy. Well, tau is easy. That's 9.55 KSI. As for the sigma x and the sigma y, well, we have two sigmas. What do we do with them? Well, they're both acting in the same direction. The sigma from the axial load is acting in compression, and the bending moment stress is acting in either compression or in tension, but they're both acting along the same axis. So I propose that one of these is going to be 0, and the other is just going to be summing these two values up. So this is 1.43 KSI plus 11.46 KSI. So this is 12.89. And so once you've got that, I think you'll see that the computation of your sigma average and radius and all of that it follows along exactly what we did in our previous problem. We just have different starting values. So I'm going to go through that process very, very quickly. So therefore, sigma average is sigma x plus sigma y over 2. One thing I forgot, actually, let me go up here. Since these are both compression, they need to be negative. So apologies for that. Since they're both compression, they need to be negative. So negative 12.89 plus 0 over 2, it's just that, half that, so that is minus 6.45 KSI. Then the radius of Moore's circle is sigma x minus sigma y over 2 squared plus tau xy squared, and then the square root of all that. So plug and chug. Give me 1 second. I'm getting 11.52. Yes. So therefore, sigma 1 is sigma average plus R, sigma 2, sigma average minus R, tau max equals R. So that one's easy. That's 11.52 KSI. So this one is 5.08. This is, one moment, minus 17.97. All right, and so again, very similar as before, our normal stress components are actually larger than our initial, or our principal stresses and maximum shear stresses are larger than our initial states of stress. So again, hopefully this really drills in that orientation really matters when you're evaluating states of stress. Okay, that's all I have for this video. You all have a wonderful break. I will see you when you get back.